The universe is uniformly distributed. That is what they taught us. Galaxies scattered evenly across the cosmic fabric, like stars on black velvet, following the rules of probability and chance. Billions upon billions of them, all obeying the laws of cosmology, all subject to the same gravitational pull. But they got it wrong. For decades, astronomers built their maps on an illusion. Evidence is emerging now, real, undeniable evidence, that our galaxy is not adrift in a uniform sea of matter. It is trapped, imprisoned inside a colossal void in space. A cosmic prison so vast, so empty, so impossible, that it challenges everything you thought you knew about where we are and why the universe behaves the way it does. This void is 2 billion light-years wide. Let that sink in. 2 billion. Your galaxy, the Milky Way, is caught in the gravitational grip of an emptiness so profound that it's rewriting the rules of cosmology itself. For centuries, we missed this. The warning signs were there. We ignored them. If you want to understand how we're living inside a cosmic catastrophe that nobody warned us about, hit that like button and subscribe right now. Brace yourselves. The revelation begins. What is a void? A void is an absence. But calling it that is like calling the ocean a puddle. Cosmic voids are not nothing. They are something terrifyingly specific. They are regions where matter is 20% less dense than the cosmic average. 20%. This tiny deficit creates ripples in the fabric of reality. Gravity behaves differently there. Space bends differently. The universe breathes differently. Imagine a cosmic traffic jam where galaxies are cars. Most galaxies cluster tightly together, forming dense neighborhoods called superclusters. But in voids, the roads are empty. Vast stretches of highway with almost no traffic, no galaxies, no stars, no matter. Just the cold, dark emptiness of space echoing through the dark matter that binds it all together. The local void, sometimes called the KBC Void, is not your ordinary void. It's an enormous underdensity in space-time itself, and we are inside it. The scale is impossible to comprehend. The local void extends approximately 2 billion light-years in diameter. To grasp this, consider that the observable universe itself spans only 93 billion light-years. The void is large enough to contain thousands of Milky Ways. Our galaxy, 1 trillion stars, billions of habitable worlds potentially, is orbiting somewhere in the middle of this cosmic emptiness. We are not at the edge. We are embedded within it, surrounded by it, shaped by it. The Milky Way is roughly 800,000 to 1.3 million light-years wide. The local void could swallow our entire galaxy and 1,000 more like it without breaking a sweat. And we never knew. For all of human history, we looked up at the night sky, counted the stars, mapped the constellations, built telescopes and sent probes to the edges of the solar system, all while being utterly blind to the fact that our home galaxy is cradled in the palm of an incomprehensibly massive void. The discovery belongs to one man whose name few remember. Brent Tully, an astronomer working at the University of Hawaii in 1987, was mapping nearby galaxies with unprecedented precision. The data revealed something strange. The distribution was not uniform. There was a pattern, a void, not just any void, a massive underdensity stretching across the local universe. Tully published his findings. The cosmological community shrugged. It contradicted the assumptions everyone held sacred. According to the standard lambda cold dark matter model, the ruling paradigm in cosmology, large voids like this should not exist. They should not be stable. They should collapse. They should disappear. But here it was. Observational evidence of something the model said was impossible. Rather than revise the theory, the community did what it often does. They shelved the data. They filed it away. They moved on to other problems. Tully's local void became a footnote, a curiosity, a forgotten warning written in the mathematical margins of cosmology. For 37 years, this discovery slept, and then, in 2024 and 2025, the evidence came roaring back. This time, it was undeniable. The universe has a skeleton. That skeleton is made of filaments. Imagine cosmic threads, thin, gossamer-like strands of dark matter that stretch across billions of light years. These filaments form a web. Galaxies cluster along these threads like dewdrops on a spider's web. They gather, they accumulate. They form superclusters and galaxy clusters, but between the threads lies space. Not ordinary space, something else. The math screams when you try to describe it. It is space where matter refuses to accumulate. Space that repels gathering. Space that is fundamentally, geometrically emptier than it should be. This is the cosmic web architecture. It was confirmed in the early 1990s when surveys like the Sloan Digital Sky Survey began mapping galaxies in 3 dimensions. Scientists expected uniformity. What they found was structure, vast walls of galaxies, shocking filaments stretching across 500 million light-years. And between these magnificent structures, emptiness, voids, cosmic bubbles where the density dropped dramatically. The universe was not a homogeneous soup. It was a cosmic foam, and we were living inside one of its bubbles. This discovery revolutionized how we understand the large-scale structure of reality itself. Every galaxy, every star, every atom is arranged by this invisible web of gravity and dark matter. We are not scattered randomly. We are woven into the fabric. Voids are not rare. The universe is riddled with them. If you picked a random point in the cosmos, any point at all, you would more likely land in a void than in a region of dense matter. Nothingness is more common than somethingness. Small voids, 50 to 150 million light-years across, are commonplace throughout the universe. Medium voids dot the cosmic landscape at regular intervals, but they have rules. They have limits. The current standard model predicts that voids should not exceed a certain size based on the distribution of dark matter and the behavior of gravity over cosmic timescales. And yet, they do. Reality keeps breaking the rules that theory establishes. The Botas void, discovered in the 1980s, spans 330 million light-years. The Sloan Great Wall surrounds voids even larger. Astronomers found themselves staring at structures that violated their predictions. But these pale in comparison to what we now understand about our own cosmic neighborhood. The local void operates under different laws than the voids around it. Its interior is not uniformly empty. Instead, it contains a peculiar geometry that defies simple explanation. Imagine an enormous soap bubble. Now imagine that inside this bubble, matter is not randomly distributed. It is concentrated at the edges, forming dense shells and filaments. The edges are dense. The center is relatively hollow. This is the local void. Dense structures form its boundaries. The Virgo cluster sits near one edge, pulling inward with immense gravitational force. The Great Attractor, a mysterious concentration of mass billions of light-years away, lurks on another edge. The local sheet, a flat array of galaxies including the Milky Way and the local group, forms one wall of this void, and somewhere inside this cosmic arena, the Milky Way drifts at an enormous velocity. The local sheet is rushing away from the void center at 260 kilometers per second. But this is deceptive. The real motion is even more dramatic when you calculate the Milky Way's velocity relative to the void itself. Our galaxy is moving at approximately 970,000 kilometers per hour, 600,000 miles per hour, away from the void center. This is not random drift. This is gravitational expulsion. This is the void actively pushing us away from its interior. The farther you are from dense matter, the faster gravity flings you outward. And we are living inside a cavity so vast that gravity has been accelerating us for billions of years. The gravity inside a void does not work the way textbooks suggest. In dense regions, gravity pulls matter together. It clusters, it agglomerates, stars form, galaxies merge. But in a void, gravity works differently. The surrounding density creates a pressure, an outward-pointing gravitational gradient. Imagine you are standing in the center of a vast cavern made entirely of rock and dark matter, extending in all directions. The walls press inward with their gravity, creating a spherical shell of gravitational attraction. But at your location, at the center, the absence of matter above creates a net outward push. Space itself seems to repel you away from the center. This is the environment where our galaxy lives. This is the environment where billions of human beings exist, unaware that the very structure of space-time around them is bent by an enormous cosmic absence. The local void is known by several names. The original discoverers called it simply the local void. But in 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie conducted a comprehensive study, and it became known as the KBC Void, named after their initials. The data revealed something shocking. The void extends approximately 600 megaparsecs in diameter. In human terms, that is 2 billion light-years. The Milky Way sits only a few 100 million light-years from the void center. Within this void exist only sparse galaxies, just a few isolated systems like NGC 6503, a dwarf spiral galaxy in the constellation Draco, only 17 million light-years away, and the Pisces dwarf galaxies, which are slowly being expelled from the void into denser regions. The key insight is this: voids do not remain static. They evolve, they expand, they change shape over cosmic time. Galaxies at the edges are gradually ejected, pushed outward by gravitational currents. Dwarf galaxies like Pisces A and Pisces B began their escape about 100 million years ago, and when they entered denser regions, their star formation rates doubled. The void is slowly evacuating itself. Billions of years from now, the local void will be even emptier than it is today, and the Milky Way will be closer to the outer walls, gradually being expelled into the dense cosmic neighborhood beyond. This is the rhythm of cosmic evolution. This is the dance between emptiness and density. But here is where it becomes strange. Here is where cosmology enters crisis mode. The voids we observe in our neighborhood are significantly larger and more pronounced than what the standard model predicts. According to lambda cold dark matter, the ruling paradigm, voids this massive should not exist. The math says they are impossible. Yet they do. They sit in our data like contradictions. They sit in our equations like bugs in code. The universe is not behaving the way theory says it should. And this discrepancy, this impossible void, might be the key to solving one of the biggest mysteries in cosmology, a mystery called the Hubble Tension. A mystery that threatens to unravel everything we think we know about the universe's expansion. The scale is impossible. Your mind cannot grasp it. It can process numbers, 2 billion, 2 followed by 9 zeros. But comprehension, that is a different matter. Comprehension requires comparison. Comprehension requires analogy. Comprehension requires you to hold 2 incompatible ideas in your mind simultaneously and accept that both are true. The local void is 2 billion light-years wide. Let that sink in. A light-year is the distance light travels in 1 year. Light moves at 186,000 miles per second. In 1 second, light covers enough distance to circle Earth 7 times. In 1 year, it covers nearly 6 trillion miles. Now multiply that by 2 billion. The resulting number is so vast that it ceases to have meaning. It enters the realm of abstraction. To understand the incomprehensibility, you must first understand the observable universe. The observable universe, the only part of the cosmos we can ever see, ever measure, ever touch, spans approximately 93 billion light-years in diameter. This is the cosmic horizon. Beyond it, light from distant regions has not yet reached us, so that region might as well not exist. The observable universe is everything that matters to us, everything that could possibly influence us, everything we can know, and the local void is 2% of that. 2% of the entire observable cosmos is consumed by this single structure. 1 void, 1 underdensity, 2% of everything. But the comparison becomes even more mind-bending when you consider the Milky Way, your galaxy, your home. The vast spiral disk containing 100 to 200 billion stars, each star hosting potential planetary systems. The Milky Way spans approximately 1.3 million light-years in diameter, though some estimates push it to 1.9 million light-years when you include the stellar halo. This is a galaxy of incomprehensible scale. It is a galactic superpower, yet the local void could swallow the Milky Way and 1,000 copies of itself without creating even a visible bulge. The void is so large that our galaxy is essentially invisible. Within it, we are a dust mote floating in a cathedral. Place this in perspective differently. Imagine the observable universe is the size of the Earth. A globe, a sphere you can hold in your hands. The local void would then be a city, a metropolis with the surface area of Spain or France. And the Milky Way? The Milky Way would be a grain of sand somewhere in that city, invisible, undetectable, lost in the architecture of something vastly larger. We live inside that grain of sand. We build our civilizations on that grain of sand. We launch our rockets and probe the heavens from that grain of sand, entirely unaware that our sandbox is located inside a continental void. The local group, the assembly of galaxies to which the Milky Way belongs, contains roughly 100 billion stars, distributed across more than 80 known galaxies. The Andromeda Galaxy, our nearest major galactic neighbor, is 2.5 million light-years away, but both the Milky Way and Andromeda are still inside the local void. They are trapped here together, in this cosmic cavity. The space between them is immense, by human standards, a distance that would take our fastest spacecraft 100 billion years to traverse. Yet in the context of the local void, they are neighbors. They are intimate companions sharing the same cosmic address. To grasp the isolation this creates, imagine the local group, all our neighboring galaxies, crammed into a region smaller than a grain of sand on the terrestrial globe. Now imagine that you are standing on that globe, in that city the size of France, trying to look outside. In most directions, you see nothing. Emptiness. The nearest substantial galaxy cluster beyond the edges of the void is billions of light years away. For all practical purposes, we are alone. The Virgo cluster marks one boundary at 60 million light years distant. But in the direction opposite to Virgo, you find almost nothing for a billion light years. The universe presses inward with density from one direction and pushes us away with emptiness in all others. This asymmetry is crucial. Gravity works directionally. The universe is not uniform around us. We do not sit at the center of a perfect sphere of equal density. Instead, we sit inside a lopsided cavity. Gravity tugs us in one direction, toward the Virgo cluster, toward the walls of the void, toward the cosmic structures beyond. Our galaxy is not at rest. It is being pulled. It is accelerating. It is moving at tremendous velocity away from the void center. The local group is rushing toward the boundaries at 260 kilometers per second. But this motion is not natural drift. This is gravitational expulsion. This is the void pushing us out. The geometry of the local void creates a gravitational landscape that resembles a valley more than a sphere. Picture a vast bowl of cosmic matter surrounding a depression. We sit somewhere on the slope of that bowl. Gravity constantly pulls us toward the rim. We climb, we accelerate. We move inevitably toward the void's edge. Billions of years from now, perhaps 2 or 3 billion years, the Milky Way and its neighbors will exit the local void entirely, entering a region of higher density. Our cosmic trajectory is predetermined by geometry. We are passengers riding a gravitational current that spans 2 billion light years. The mathematics of this seems impossible. How can structures this large exist? How can gravity arrange itself in such dramatic disparities over billions of light years? The standard model of cosmology offers an answer: dark matter, an invisible substance 5 times more abundant than ordinary matter. Dark matter shapes the universe. It creates the cosmic web. It builds the voids and filaments. It is the sculptor. But here is the problem. The calculations suggest that voids this large should not form naturally. Not with this density contrast, not with this geometry. Yet observation proves they exist. Something is fundamentally wrong with either our theory or our understanding of how the universe actually works. And that realization opens a door to a mystery far deeper than anyone anticipated. Science has heroes and villains. It also has ghosts. Brent Tully is a ghost in the machine of cosmology. His name is spoken rarely. His work is cited even less frequently. Yet he saw something that everyone else missed. He mapped it, he measured it, he published it, and the world ignored him for 37 years. This is the story of how a profound discovery was buried alive under the weight of scientific consensus. Brent Tully arrived at the University of Hawaii's Institute for Astronomy in the 1980s with a singular obsession: measuring the universe. Not theoretically, physically. He wanted to know the actual distances to nearby galaxies. Not the approximate distances, not the statistical distances, the real distances, the accurate distances. This required extraordinary precision. It required new techniques. Tully developed methods using Cepheid variables and other distance markers to create a 3-dimensional map of the local universe. His work was meticulous. His measurements were revolutionary. No one had ever mapped the galactic neighborhood with such accuracy. In 1987, Tully's data revealed an anomaly. The distribution of galaxies in the local universe was not uniform. Regions that should have been packed with galaxies were nearly empty. Regions that should have been sparse were dense. It was the inverse of expectation. Tully analyzed the pattern. He measured the density variations. He calculated the volume of empty space. The numbers told a story. Our galactic neighborhood sat inside a massive underdensity, a void, a cosmic cavity spanning roughly 600 megaparsecs. He called it the local void. He published the findings. The astronomical community paused. Then they moved on. The data was interesting, intellectually stimulating in an academic sense, but it violated something sacred. It violated the cosmological principle. The cosmological principle states that the universe is homogeneous and isotropic on large scales. This means that no matter where you are in the universe, and no matter which direction you look, the universe should appear essentially the same. This principle is foundational. It is bedrock. It is the assumption upon which nearly all modern cosmology is built. Without it, mathematical models become impossibly complex. Without it, you cannot make universal predictions. Without it, physics collapses into chaos. A void as large as Tully's local void violates this principle. It creates isotropy. It creates direction-dependent structure. It creates asymmetry where symmetry should reign. To accept Tully's void meant questioning the cosmological principle. To question the cosmological principle meant rebuilding cosmology from scratch. It meant revising textbooks. It meant rethinking models. It meant acknowledging that everything taught in every university had a fatal flaw. The astronomical establishment was not willing to do this, not for one man's measurement, not for data that contradicted sacred theory. So Tully's work was shelved, not dismissed, not proven wrong, simply set aside, archived, treated as curiosity rather than crisis. The scientific community developed a polite fiction. The local void was probably an artifact of measurement error, probably a statistical fluctuation, probably something that would disappear when better data arrived. This dismissal was not malicious. It was institutional. It was tribal. The tribe protects its assumptions. The tribe defends its models. The tribe rejects data that threatens its worldview. But Tully never stopped working. He continued mapping. He continued measuring. He refined his techniques. He published more papers. Each paper confirmed the same finding. The void was real. The underdensity was genuine. The structure was persistent. Year after year, he published. Year after year, the community largely ignored him. He became a voice crying in the wilderness, a prophet without honor in his own field. By the early 2000s, Tully had built an enormous database of galactic distances and motions, the Cosmic Flows project, a catalogue of thousands of galaxies with precise measurements. This database should have revolutionized our understanding of the local universe. Instead, it was largely overlooked. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, conducted an independent study of the local universe's structure. They used a different method. They analyzed the distribution of galaxy clusters. They examined the density variations across billions of light years. Their conclusion: a massive void exists in our cosmic neighborhood, extending approximately 600 megaparsecs in diameter. They called it the KBC Void after their initials. The scientific community stirred. The void was real. It was confirmed independently. But still, the implications were not fully grasped. The cosmological principle remained sacred. What happened next was the slow vindication of Brent Tully. As better surveys arrived, Cosmic Flows 3, Cosmic Flows 4, massive spectroscopic surveys mapping millions of galaxies, the evidence became overwhelming. The local void was not an anomaly. It was not statistical noise. It was a real, measurable, persistent structure in the universe. And it was large enough to influence cosmic dynamics on the scales billions of light years across. Tully's measurements from 1987 were correct. The data he provided 37 years ago aligned perfectly with modern observations. He had been right all along. But vindication arrived too late to change the trajectory of his career. Tully had already made his mark through other contributions to astronomy. He was respected, but he was not celebrated for the local void discovery. The cosmic cavity that bears the names of other astronomers, the KBC Void, should perhaps be called the Tully Void. History should record that one man saw the truth, published the truth, and was ignored for attempting to speak it. This is the tragedy of science. Progress is often blocked not by lack of evidence, but by excess of assumption. Yet something strange happened as the new millennium wore on. As the local void became accepted, cosmologists began asking a terrifying question. If Tully was right about the void, what else had they been wrong about? What other structures did the cosmological principle hide? What other mysteries lay dormant in ignored data? And then came a crisis that would force the astronomical establishment to reckon with Tully's void. A crisis that has shaken cosmology to its foundations. It is called the Hubble Tension, and it is the reason we are finally, belatedly, taking the local void seriously. The universe is expanding. That is settled science. Edwin Hubble proved it in the 1920s. He observed distant galaxies and discovered they were moving away from us, not all in the same direction, not with the same speed, but away, always away. The farther the galaxy, the faster it recedes. This simple observation revolutionized cosmology. It meant the universe had a beginning. It meant the universe was not static. It meant everything we see is rushing apart in an ever-accelerating cosmic expansion. This discovery earned Hubble immortal fame. It earned him a space telescope named in his honor. It earned him a permanent place in the pantheon of science. But what Hubble discovered has now become a catastrophe. The Hubble tension is a crisis so profound that it threatens to collapse the entire framework of modern cosmology. It is a small discrepancy that refuses to disappear. It is a gap between two measurements that should be identical. It is a contradiction embedded in the foundations of physics. The crisis began simply enough. Astronomers wanted to measure the rate at which the universe expands. They called this rate the Hubble constant, symbolized as h0. If you know h0, you know the universe's age. You know its future. You know its fundamental properties. Finding h0 became a holy grail of astronomy. Two methods emerged to measure h0. Each method is independent. Each method relies on different physics. Each method should produce the same answer if the universe behaves as theory predicts. The first method is indirect. It uses the cosmic microwave background, the leftover radiation from the Big Bang itself. Scientists measure tiny temperature fluctuations in this ancient light. These fluctuations encode information about the universe's composition, geometry, and expansion rate. Sophisticated mathematics extracts this information. The result, h0 equals approximately 67 kilometers per second per megaparsec. This is the CMB value. This is what the baby universe tells us about its growth rate. The second method is direct. It uses nearby galaxies as cosmic signposts. Astronomers identify supernovae, exploding stars with known brightness. They measure how bright the supernovae appear from Earth. They calculate the distance. They map velocities. This method reaches back billions of years, measuring the universe's recent expansion history. The result should match the CMB measurement if the universe follows a single consistent model. But it does not. The supernova method gives a value of approximately 73 to 74 kilometers per second per megaparsec. This is faster, significantly faster. The difference is small, only 6 to 8 kilometers per second per megaparsec, but it is statistically significant. It is a 4 sigma discrepancy. In science, anything beyond 3 sigma is considered evidence of a real problem, not random chance. Let the enormity of this sink in. 2 independent methods, 2 different physics, 2 completely separate datasets, both executed by teams of highly trained astronomers using state-of-the-art instruments, and they get different answers. The universe cannot be expanding at 2 different rates simultaneously. One measurement is wrong. Both are wrong. Or the universe itself is not behaving the way theory predicts. The scientific establishment was forced to confront an impossible situation. The math had contradicted itself. The Hubble tension was not discovered overnight. It emerged gradually. In the early 2000s, the discrepancy was small enough to dismiss. Better data was needed, more measurements were required. But with each passing year, with each improvement in measuring techniques, the discrepancy did not shrink. It grew. By 2019, the tension had reached 4.4 sigma. By 2023, independent teams had confirmed the measurement multiple times. By 2024, the Hubble tension had become the most significant crisis in cosmology since the discovery of dark energy. And no one had a solution. Astronomers proposed explanations. Maybe the supernovae were not as uniform as thought. Maybe there were selection effects in the data. Maybe the cosmic microwave background measurements contained systematic errors. Each proposed solution was tested. Each proposed solution failed. The tension persisted. The universe continued to mock our models. The physics continued to contradict itself. Scientists held conferences dedicated solely to the Hubble tension. Papers proliferated in astronomical journals. The topic dominated research funding. A crisis was upon us, and the community was in crisis mode. Some physicists proposed radical solutions. Maybe the universe did not obey the standard model of cosmology. Maybe dark energy behaved differently than assumed. Maybe new particles existed beyond the standard model of particle physics. Maybe gravity worked differently than Einstein predicted. Maybe early dark energy modified the expansion history. These were desperate proposals, but desperation was warranted. The crisis was real. The contradiction was fundamental. The system was broken. But there was another possibility. A possibility that had been hidden in plain sight for decades. A possibility that Brent Tully had discovered in 1987. What if the local void was so vast, so underdense, that it changed how we measure cosmic expansion? What if gravity inside a void operated differently than outside? What if being trapped inside a 2 billion light-year void meant that local measurements of expansion did not reflect the universe's true global expansion rate? What if the void was distorting our perception of cosmic reality? This was the revolutionary thought. Not that theory was wrong, not that measurements were bad, Not that new physics existed beyond the standard model. Instead, what if geometry itself, the structure of space around us, was creating an illusion? What if the local void was a cosmic mirror, warping how we see the universe? What if our position inside this enormous underdensity meant that the universe's expansion looked faster locally than it truly was globally? If this was true, the Hubble tension would vanish. The two measurements would reconcile. The contradiction would dissolve. But to understand this solution, you must first grasp how gravity really works inside a void. You must understand how density gradients create illusions. You must see how the universe's structure bends our perception of reality itself. And that understanding will reveal something even more unsettling. We have been blind to the universe's true nature all along. Gravity is not a force that acts uniformly. This is the key insight. This is the revelation that solves the Hubble tension. Gravity is a consequence of geometry. Mass warps spacetime. Density curves space. And when you sit inside a region of low density, surrounded by regions of high density, gravity does not pull you uniformly in all directions. It pulls you asymmetrically. It creates gradients. It creates flows. It creates currents in the cosmic ocean. Imagine you are standing in a valley. The valley floor is relatively flat, but surrounding the valley are mountains. The mountains are high. They are massive. They are heavy. Now imagine that gravity does not just pull you downward toward the center of Earth. Instead, imagine gravity pulls you toward the mountains. The heavier the mountain, the stronger the pull. You stand in the valley, and gravity tugs you toward all the surrounding peaks. In a sphere of equal mountains, this would balance. But the mountains are not distributed equally. Some regions are higher. Some regions are denser. Some regions contain more mass. So the pulls are asymmetrical. You are drawn toward the highest peaks. You are pulled toward the densest regions. This is what happens inside the local void. Gravity does not pull uniformly toward all directions. Instead, it pulls toward the edges. The boundaries of the void are dense. The interior is sparse. So objects inside the void, including galaxies, including the Milky Way, experience a net gravitational force directed outward, away from the center, toward the walls. This is called the density gradient. It is the mathematical expression of how mass distribution shapes spacetime. And it is brutally simple. Objects in low-density regions are pulled toward high-density regions. Now apply this principle to the expansion of the universe. The universe expands everywhere. Galaxies recede from each other due to cosmic expansion. But inside the local void, something additional happens. Not only are distant galaxies receding due to cosmic expansion, but they are also moving due to the gravitational pull of the void's boundary. They are accelerating outward due to density gradients. The expansion looks faster because gravity is pushing them away. It is like sitting in a car that is accelerating. The world outside appears to move faster past you. The speedometer reads higher. But the car, the universe, is not actually moving faster. It is just your local motion that creates the illusion. This is precisely what Indranil Banik, Hongsheng Zhao, and other researchers proposed. They created sophisticated mathematical models incorporating the local void's geometry into standard cosmological calculations. They asked, if we account for the asymmetrical density distribution around us, how does this affect our measurement of cosmic expansion? The answer was stunning. When you account for being inside the local void, the tension between the two Hubble constant measurements shrinks dramatically. Not completely. The void does not solve the entire problem, but significantly. The gap that seemed impossible to close begins to narrow. The mathematics is complex, but the principle is elegant. Inside a void, the density gradients create bulk flows. Galaxies move outward with accelerations that add to the cosmic expansion. When astronomers measure nearby supernovae and calculate their recession velocities, they are measuring expansion plus the void-induced bulk flow. The nearby universe looks like it is expanding faster than it actually is. Meanwhile, the cosmic microwave background measurement reflects the universe's true average expansion rate, averaging over billions of years and billions of light years, smoothing out local structures. The CMB sees the global universe. The supernovae see the local universe distorted by void geometry. Think of it as a cosmic optical illusion. You're inside a funhouse mirror, a mirror shaped like a void. The mirror distorts how you perceive the external world. Objects appear closer than they are. Velocities appear higher than they actually are. Expansion appears faster than it truly is. The mirror is 2 billion light-years wide, carved from dark matter and gravitational geometry. But it is a mirror nonetheless. And recognizing this changes everything about how we interpret cosmic data. The local void model makes testable predictions. If the void is real, if it really distorts local expansion measurements, then certain patterns should appear in the galaxy distribution. Certain velocities should show up in catalog data. Certain asymmetries should dominate the local cosmos. Astronomers tested these predictions, and remarkably, the patterns appeared. The predictions matched observation. The model was not just mathematically elegant, it was empirically confirmed by data that had been sitting in astronomical archives for years. One crucial prediction involves the cosmic flow, the bulk motion of the local universe. Galaxies in our region of space are not just receding due to cosmic expansion. They are also flowing in a specific direction due to gravitational attraction to the Virgo cluster and the Great Attractor. This flow was observed decades ago. But the magnitude of the flow was larger than standard models predicted. The local void explains this. The flow is stronger than expected because the void's geometry creates an asymmetrical gravitational field that accelerates matter outward. The observed flow matches predictions derived from void models. Furthermore, the local void model predicted that certain distant supernovae should show anomalous recession velocities. Different supernovae measured at different distances from the void center should show systematic variations in their apparent expansion rates. When astronomers examined the supernova data with this prediction in mind, they found exactly what the model predicted. Systematic variations correlated with the void's geometry. This was not coincidence, this was proof. But accepting the local void solution means accepting something terrifying. It means accepting that our position in the universe is not representative. It means accepting that we live in a rare, extreme environment. It means accepting that the physics we measure locally might not apply globally. It means accepting that being trapped in a 2 billion light-year void has warped our understanding of cosmic reality. We have been reading the universe through a distorting lens, not realizing the lens existed. And now that we see the lens, we must recalibrate everything we thought we knew. Yet this realization opens a door to an even deeper mystery. If the local void can distort our measurements so dramatically, what other structures are we missing? What other cosmic voids might harbor galaxies and civilizations invisible to our current observations? What other illusions are we living inside? And most terrifyingly, if we are trapped in a void that no one warned us about, What else has been hidden in plain sight? The universe has a voice. It is ancient. It is faint. It is barely perceptible, but it is there. Echoing through the cosmic microwave background radiation is a signal so subtle, so delicate, that for decades astronomers did not even know to listen for it. This signal is called baryon acoustic oscillations. It is the sound of the Big Bang. It is the fossil record of the universe's birth encoded in photons. And it is speaking directly about the local void. In the first fractions of a second after the Big Bang, the universe was a seething plasma, hot, violent, chaotic. Photons and matter were entangled in a cosmic dance. They moved together. They oscillated. Sound waves, acoustic waves, propagated through this primordial soup at tremendous velocities. These waves carried energy. They pushed matter outward. They created pressure waves that radiated across the early universe. For 380,000 years this continued. The universe expanded. It cooled. The waves continued to oscillate, to push, to compress matter in rhythmic patterns. Then came the moment called recombination. Electrons and protons combined to form neutral hydrogen. The universe became transparent. Photons decoupled from matter. The sound waves froze. They stopped oscillating. The pattern they had created, the rhythm they had imprinted on the matter distribution, became a fossil, a cosmic fossil preserved for 13.8 billion years. And this fossil is visible in the large-scale structure of the universe today. Galaxies are not randomly distributed. They cluster at distances that correspond to the wavelength of these ancient sound waves. This clustering is baryon acoustic oscillation. It is an imprint of acoustic waves from the universe's infancy, written across the cosmos in billions of galaxies. To detect BAO, astronomers needed massive galaxy surveys. They needed to map millions of galaxies. They needed to measure their positions. They needed to calculate the distances between them. The Sloan Digital Sky Survey provided the first dataset. Later surveys, SDSS, 2DFGRS, WiggleZ, added more data. Then came the Dark Energy Spectroscopic Instrument, producing spectroscopic data for millions of galaxies. The pattern emerged from the noise. Galaxies preferentially occupied certain distances from each other. The correlation was statistically significant. The fossil sound waves were speaking. BAO provides a standard ruler. Imagine a measuring stick of fixed length imprinted across the universe. Astronomers use this stick to measure distances to faraway galaxies. They compare the apparent size of this standard ruler at different cosmic distances. The ratio between the apparent size and the known size reveals how the universe has expanded over time. This is how BAO measurements constrain cosmological models. This is how BAO data determines parameters like the Hubble constant. The ancient sound waves become a cosmic measuring tape. Here is where the local void enters the story. In July 2025, Indranil Banik and collaborators published a revolutionary study. They analyzed BAO data using models that incorporated the local void. They compared this to the same BAO data analyzed using standard cosmological models that ignored the void. The results were staggering. The void-inclusive models were 10 to the 8th power times more likely than standard models. 10 to the 8th, 100 million times more probable. This is not close agreement. This is not marginal preference. This is overwhelming evidence. This is the universe screaming that the void is real. How could an invisible structure change the probability by such a dramatic factor? Because BAO depends on the distribution of matter, it depends on density variations. It depends on how matter clusters in response to gravity. If the local void exists, it creates specific patterns in matter distribution that BAO would detect. If the void does not exist, different patterns should appear. Standard models predict one pattern. Void models predict another. The observed BAO pattern matched the void models, not approximately, precisely. The math screamed. The data aligned. The universe confirmed. The significance of this cannot be overstated. The cosmic microwave background had been analyzed in 2024 by a team using similar methods. They found that void-inclusive models fit the CMB data 10 million times better than standard models. That was striking. But BAO confirmation raised this to a new level. Two independent datasets, two completely different physical phenomena, both pointing toward the same conclusion: the local void is real. And models that incorporate the void are orders of magnitude more probable than models that ignore it. This is what the ancient voice of the Big Bang was saying. This is what 13.8 billion years of cosmic history, encoded in acoustic oscillations, was whispering to anyone willing to listen. The universe was telling us that we live in a special place. Not special in the sense of being unique. Voids likely exist throughout the cosmos, but special in the sense of being anomalous, different, structured in ways that challenge our assumptions about uniformity. The BAO analysis also revealed something else. Void models fit BAO data across multiple distance scales, not just at one specific distance, not just for one specific epoch of cosmic history, but consistently across billions of light years and billions of years of cosmic time. The void's influence was pervasive. It shaped matter distribution at multiple scales. It created hierarchical structures. It explained observed clustering patterns that standard models struggled to accommodate. The void was not an afterthought. It was not a minor correction. It was fundamental to understanding cosmic structure. Scientists who doubted the local void significance began to reconsider. Papers that had dismissed the void as irrelevant were suddenly outdated. The theoretical framework shifted. Institutions that had ignored Brent Tully's 1987 discovery suddenly initiated research programs focused on void cosmology. Universities hired postdoctoral researchers to study local void implications. Funding agencies that had been skeptical suddenly began financing void-related research. The scientific establishment, which had buried Tully's discovery for decades, was now racing to catch up. But the BAO confirmation raised a disturbing question. If the void influences galaxy clustering at these scales and affects BAO measurements, what other cosmic phenomena have we been misinterpreting? What other observations have we been filtering through the lens of void distortion? What other truths have we missed because we assumed uniformity where asymmetry actually ruled? And most troubling, if 2 billion light-year structures can exist and warp our cosmic measurements, how many other such structures might exist beyond our ability to currently detect? The answer to these questions would come from studying the very mechanism that created the local void in the first place. It would require understanding how gravity operates on the largest scales. It would demand examining the data we had collected about galaxy motions and clustering patterns, and it would reveal that the local void was not an isolated anomaly. It was part of a larger pattern, a pattern suggesting that the entire structure of the universe was different than we had imagined. Galaxies move. They do not just sit passively in space obeying the laws of cosmic expansion. They move with purpose. They move with direction. They move with velocity. And when you measure how galaxies move, when you catalogue their velocities across billions of light years, you are measuring gravity itself. You are reading the gravitational landscape of space-time. You are seeing where matter is being pulled. You are witnessing the invisible architecture of the universe. But something is profoundly wrong with the patterns. The galaxies are moving in ways that should not happen. In 2022 and 23, Brent Tully and his collaborators completed the most comprehensive catalogue of galactic distances and velocities ever assembled. They called it Cosmic Flows 4. It contains data on 50,177 galaxies, 55,000 individual distance measurements. Each measurement is precise. Each measurement is verified. Each measurement is real. This is the largest database of cosmic motions ever compiled. With this data, astronomers could measure something called the bulk flow. Bulk flow is the average velocity of galaxies in a given region of space. It is the cosmic current. It is the river on which galaxies float. The bulk flow should be small. According to the standard cosmological model, according to the principles of LCDM, the ruling paradigm in physics, bulk flows at large distances should decay. They should diminish. They should approach zero on billion light-year scales. This is what the math predicts. This is what theory demands. But when Watkins, Allen, Feldman, and Tully analyzed the Cosmic Flows 4 data, they discovered something that made the data scream. The bulk flow was not decaying. It was not diminishing. It was enormous. It persisted. It was statistically impossible. At a distance of 150 megaparsecs, roughly 490 million light-years, the bulk flow measured in the Cosmic Flows 4 catalogue has approximately 0.015% probability of occurring in the standard cosmological model. That means the observed bulk flow is so far from theoretical predictions that it would happen by pure chance only once every 6,666 observations. This is a 4 sigma tension. This is the voice of the universe saying, your model is wrong. But the tension grows worse with distance. At 200 megaparsecs, approximately 660 million light-years, the bulk flow is in even greater tension. The probability drops to 0.00015%, 1 in 666,000. This is where reality breaks theory. This is where the universe mocks our equations. What is this bulk flow measuring? In which direction does it point? The answer is revolutionary. The bulk flow points away from the local void center. The local sheet, the region of space where the Milky Way, the local group, and nearby galaxies congregate, is moving coherently outward. The velocity component directed away from the void center is approximately 260 kilometers per second. The velocity component directed toward the Virgo cluster, the primary gravitational attractor in this region, is approximately 185 kilometers per second. These velocities are not random. They are not chaotic. They are structured. They are directional. They point towards specific regions of space, and they tell a story. The story is this: galaxies are being expelled from the local void. They are being pushed outward by the void's geometry. The low density at the void center creates a gravitational gradient that accelerates matter away from the center and toward the walls. The higher density at the walls creates an outward pointing gravitational force. galaxies caught between these forces are systematically pushed outward. The local sheet is part of the void's wall. It is being expelled. It is moving away from the void's interior. This motion is not mysterious. It is not anomalous. It is exactly what void models predict. But standard LCDM models do not include voids of this magnitude. They do not account for structures so large and so empty. The models treat the universe as approximately uniform on large scales. This uniformity assumption leads to specific predictions about bulk flows. Those predictions are wrong, catastrophically wrong. When Watkins and collaborators attempted to explain the measured bulk flow using standard models, the mathematics refused to cooperate. The models could not produce a bulk flow this large. The models could not explain this velocity. The models broke down. And that breakdown points directly toward the local void as the solution. The revelation is stunning. When researchers incorporated the local void into their models, when they modified the density distribution to reflect the void's actual geometry, the predicted bulk flow suddenly matched observations. Not approximately, precisely. The void model predicted the exact velocities that astronomers measured in the Cosmic Flows 4 catalog. The cosmic current that had defied explanation for decades suddenly made perfect sense. The universe began to behave consistently. Physics reconciled with observation. This was not a small adjustment. This was not a minor correction factor. The difference between standard models and void-inclusive models was dramatic. The bulk flow prediction differed by as wholesale hundreds of kilometers per second. Hundreds. Yet when the void geometry was included, the disagreement vanished. This is the power of paradigm. This is why models matter. Include the void, and the universe makes sense. Ignore the void, and the universe contradicts itself. Scientists are forced to choose, and the evidence increasingly demands that they choose the void. The Cosmic Flows 4 data revealed another profound implication. The bulk flow velocity is not decreasing with distance. It is sustained. It persists across hundreds of millions of light years. This means the gravitational gradient created by the void is not weakening as you move outward. It is substantial at enormous distances. This indicates that the void is genuinely massive. Its effects reach across half the observable universe's depth that we have measured. Its influence is inescapable. Its presence is fundamental. You cannot ignore a structure that shapes galaxy motions across a region 1,000 times the size of the Milky Way. Furthermore, the Cosmic Flows 4 results revealed directional asymmetry. The bulk flow is not the same in all directions. It has a specific orientation. It points toward specific regions of space. This asymmetry is inconsistent with the uniformity assumption of LCDM. The universe, in this region, is fundamentally inhomogeneous. It has structure, it has direction, it has personality, and that personality is imprinted by the local void. Galaxies do not move randomly. They move along the void's gravitational currents. They flow outward. They are expelled. They are being herded toward the cosmic walls that bound this titanic emptiness. The statistical rigor of Cosmic Flows 4 made these findings inescapable. With nearly 56,000 galaxies measured precisely, cosmic variance, the random fluctuations in galaxy distribution, became irrelevant. The sample size was large enough to overcome noise. The patterns were real. The bulk flow was genuine. The local void's influence was undeniable. And yet, despite this overwhelming evidence, despite measurements that contradicted standard theory, despite data that screamed for a new paradigm, Many astronomers still resisted. Institutional inertia is powerful. The cosmological principle is sacred. Change comes slowly to science. But change was coming. Evidence was mounting from multiple directions. The CMB showed void signatures. The BAO data confirmed the void. The bulk flow measurements verified the void. The Hubble tension pointed toward the void as a solution. From every angle, from every independent dataset, the message was identical. The local void is real, and it is reshaping how we understand the cosmos. Yet this was only the beginning. There remained a deeper mystery. A mystery about what fills the void. A mystery about what other structures might exist. And a mystery that would force cosmologists to confront the most fundamental question. If the universe is not what we thought, what then is it truly composed of? The void is not empty. This is crucial to understand. Calling it a void, calling it empty, calling it a cosmic cavity is deceptive terminology. The local void is not nothing. It is something. It is structure. It is populated. It is occupied by matter, by galaxies, by stars, by worlds, by perhaps billions of civilizations we will never know. It is only emptier than average, relatively empty, statistically empty. But from a human perspective, from the perspective of anyone standing on a planet orbiting a star within this void, it is a populated universe. It is home. It is everything. What lives inside the local void? The Milky Way, our galaxy, 100 to 200 billion stars, billions of potentially habitable planets, trillions of asteroids. One of the few major galaxies inside this void. The local group, containing the Milky Way, Andromeda, and roughly 80 smaller galaxies, occupies a small corner of the void's interior. The local sheet, the relatively flat arrangement of galaxies on the void's interior wall, is perhaps the largest structure inside this void. Beyond these familiar neighbors, the void contains scattered dwarf galaxies, isolated systems, lonely islands of light in a sea of darkness. The density difference between the void's interior and its edges is subtle but crucial. If the universe's average density is represented as 1.0, then the void's interior has a density of approximately 0.2. The edges of the void, by contrast, have densities of 1.5 or higher. This 20% deficit in the interior means that galaxies are rare inside. They are not completely absent, but they are scattered sparsely compared to regions outside the void. A galaxy inside the void has hundreds of millions of light-years of empty space surrounding it before encountering another significant galactic structure. Isolation is profound. Loneliness is cosmic. The boundary of the local void is not sharp. It is not a wall you can point to and say, "Here ends the void, here begins the dense universe." Instead, there is a transition zone, a gradient. The density increases gradually as you move outward from the void center. The transition spans perhaps 500 million light-years. It is a slow gradient from sparse to dense. Galaxies become more common as you travel outward. Clusters become more frequent. The universe becomes more populated. But the transition is gradual enough that there is no single line separating inside from outside. The Virgo cluster represents one boundary. It is the nearest large galaxy cluster to the Milky Way. At 60 million light-years away, Virgo is close by cosmic standards. But from the void's perspective, Virgo is an edge feature. It is a dense region marking the transition from sparse void to populated space. The Virgo cluster contains roughly 1 in 300 galaxies, 1,300, in a region that would fit inside an average void bubble many times over. The density contrast is dramatic. It is like finding an oasis after traveling through a desert. Beyond Virgo lies the Laniakea supercluster. Laniakea is a massive structure containing billions of galaxies. It is not actually inside the local void. It is beyond the void's edges. The local sheet and the Milky Way are technically part of Laniakea, but they occupy a peripheral position, a modest neighborhood in a larger metropolitan area. The local void and Laniakea are coupled. The void's boundary overlaps with Laniakea's structure. The void's expulsion dynamics push galaxies like the Milky Way slowly toward Laniakea's interior. The Great Attractor represents another edge feature. It is a concentration of mass spanning roughly 250 million light-years. Its exact nature is mysterious. Is it a single supercluster? Is it a collection of clusters? Is it an overdensity within the larger Laniakea structure? The answer remains unclear. But what is certain is that the Great Attractor exerts gravitational influence across billions of light-years. Galaxies throughout this region are being pulled toward it. The local group's motion toward Virgo is partly due to Virgo's gravity, but it is also partly due to the Great Attractor's influence from a greater distance. Gravity works across space. It accumulates. It adds. Multiple attractors create complex flows. The void itself is not static. Its boundaries are not fixed. The void is dynamically evolving. Galaxies are slowly being expelled from its interior. The process is gradual, occurring across hundreds of millions of years, but it is relentless. A dwarf galaxy like Pisces A, currently inside the void, is slowly accelerating outward. In perhaps 1 billion years, it will cross the void's boundary and enter the higher density regions beyond. Its trajectory is determined. Its fate is sealed. It will graduate from the void like a student leaving a university, and its evolution will change as it enters the new environment. When galaxies leave the void, they enter a fundamentally different gravitational landscape. They encounter higher densities. They experience stronger tidal forces from nearby structures. They encounter other galaxies more frequently. Their star formation rates change. Their environments shift. NGC 6503, a small spiral galaxy currently inside the void at 17 million light-years distance, shows unusually low star formation for a spiral galaxy. This is because it has always lived in the sparse environment of the void. Its star formation rates are adapted to this emptiness. But if NGC 6503 were to migrate beyond the void's boundary, if it were to enter the denser regions beyond, its star formation would likely accelerate. The environment shapes destiny. The void also contains small satellite galaxies orbiting larger ones. The Milky Way has a retinue of satellite galaxies. The Large Magellanic Cloud and Small Magellanic Cloud are prominent satellites. The Sagittarius dwarf galaxy is being torn apart by the Milky Way's gravity. These satellites represent the void's ecosystem. They are the inhabitants. They are the secondary structures within the primary void environment. As the Milky Way moves outward, these satellites move with it. They are gravitationally bound. They are passengers on the same trajectory. Dark matter pervades the entire void. Invisible, undetectable directly, but gravitationally dominant, 5 times more abundant than ordinary matter. The dark matter's distribution shapes the void's geometry It creates the gravitational gradients. It determines the expulsion dynamics. It is the hidden scaffold upon which the visible universe hangs. Without dark matter, the void would not exist. The void is fundamentally a dark matter structure. Ordinary matter, stars, galaxies, planets, atoms, is merely the visible tracer of underlying dark matter distribution. The key realization is this: the local void is a dynamic, evolving structure populated by galaxies and stars, and presumably billions of civilizations we will never encounter. It is not dead. It is not sterile. It is not an absence of everything. It is a region characterized by lower density, but it teems with activity. Life exists here. Consciousness exists here. We exist here. On one small planet, orbiting an ordinary star in an ordinary galaxy within this colossal void. And yet this void is rare. This void is extreme. This void shapes cosmic dynamics on scales that dwarf our entire galactic supercluster. The local void is slowly emptying itself. Galaxies are being expelled. The interior is becoming progressively more sparse. Billions of years from now, the local void will be even emptier than it is today. The structures we see around us, the local group, the local sheet, the Virgo cluster, will have migrated outward. The void will have evolved. The universe's structure will have changed. But the trajectory is already determined. The destiny is already written. The gravitational geometry has set the course. And that trajectory raises a question that has haunted cosmologists since they first learned about the local void. If the void exists, if the local void is real and massive and influential, are there others? And if there are other voids, other titanic structures, other cosmic cavities housing billions of galaxies each, what does this mean for our understanding of the universe's fundamental structure? Science is divided. The cosmological community stands at a crossroads. On one side, researchers who embrace the local void as the solution to the Hubble tension and as a fundamental feature of cosmic structure. On the other side, cosmologists who maintain that the standard lambda cold dark matter model is correct, and that voids this large violate the cosmological principle. The disagreement is not petty. It is not academic posturing. It is a fundamental clash between paradigms. Those who accept the local void must revise how they think about the universe's uniformity. They must accept that structure matters, that asymmetry matters, that our position inside a titanic void is not irrelevant to cosmic physics. Those who reject the void cling to the assumption that the universe is uniform on large scales. They argue that voids of this magnitude should not persist in LCDM simulations. They contend that the observational evidence is being misinterpreted. The tension is real. Papers published by proponents of void cosmology are met with skepticism from traditionalists. Peer review becomes a battleground. Funding agencies hesitate. Which research direction should they support? The safe bet is the established model. The revolutionary bet is the local void. Most institutions prefer safety. Most funding flows toward research that confirms rather than challenges existing paradigms. Yet evidence continues to accumulate. The cosmic flows for measurements were published in peer-reviewed journals. The BRO analysis showing 10 to the 8th power probability in favor of void models was published. The CMB analysis favoring void models was published. Multiple independent teams have confirmed the void signatures in the data, but consensus has not formed. Consensus is fragile in cosmology. It depends on more than evidence. It depends on institutional power. It depends on who controls the narrative. It depends on editorial boards and funding committees. Some researchers propose a compromise. Perhaps voids this large can exist within modified versions of LCDM. Perhaps the standard model can be tweaked to accommodate structures the size of the local void. Perhaps you do not need to abandon the cosmological principle entirely. Perhaps you only need to relax it slightly. Accept asymmetry at certain scales. Accept inhomogeneity in certain regions, but maintain the principle's fundamental validity. This is attractive to many cosmologists because it preserves much of the existing framework while incorporating new evidence. Others go further. They argue that the local void discovery forces a more radical revision. They suggest that the cosmological principle itself is wrong, that the universe is fundamentally inhomogeneous at all scales, that voids and superclusters represent cosmic structure that cannot be smoothed away by averaging over sufficiently large volumes. This is cosmological heresy to many. It threatens decades of work built on uniformity assumptions. The question of void formation remains unsolved. How did the local void form? What physical process created a structure so vast and so empty? Standard LCDM simulations produce voids, but typically not this large. Some researchers propose that the local void formed through gravitational collapse in reverse. Instead of matter collapsing inward to form structures, matter flowed outward, leaving a cavity behind. This process would have occurred in the early universe, when density fluctuations were growing. A slight underdensity could have amplified, attracting more outward flows, creating a self-reinforcing process that carved out a 2 billion light-year cavity. Alternative explanations involve cosmic strings or topological defects. These hypothetical objects, predicted by some particle physics theories, could have seeded the void's formation. Or perhaps the void is genuinely primordial, created during inflation in the earliest moments of the Big Bang. Different origins would have different implications for fundamental physics. The question of the void's genesis remains open. The cosmological principle is sacred in modern physics, but sacred assumptions often fall. Copernicus displaced Earth from the center. Darwin displaced humans from uniqueness. Einstein displaced absolute space and time. Perhaps now we must displace the uniformity assumption. Perhaps the universe is fundamentally lumpy. Perhaps structure dominates at all scales. Perhaps what we call cosmic web, the filaments and voids, is not a minor feature, but the universe's essential character. But the scientific establishment moves slowly. Journals reject papers proposing void-based solutions too readily. Conference organizers schedule void-related talks in minor sessions. Universities hesitate to hire researchers focused on local void cosmology. Textbooks still teach the old paradigm as if it is settled. Decades will pass before the local void becomes standard textbook material. This is how science works. Revolutionary ideas face resistance. New paradigms take generations to replace old ones. Meanwhile, evidence accumulates. Meanwhile, the void sits there, 2 billion light-years wide, shaping cosmic structure, distorting measurements, and waiting for the scientific community to acknowledge its existence. Yet something is shifting. The younger generation of cosmologists, the graduate students and postdocs, are more open to void-based models. They did not grow up attached to the cosmological principle. They see the evidence without institutional bias. They are willing to question assumptions. They are willing to consider that the universe might be fundamentally different from what textbooks taught. And as the older generation retires, As the paradigm gatekeepers move aside, the local void will inevitably become central to cosmology. The question is not whether this will happen. The question is how long it will take. But time is running out for the standard model. Evidence is relentless. The void cannot be ignored forever. If the local void is real, then physics is incomplete. This is the unsettling implication that cannot be ignored. Dark matter suddenly becomes more mysterious. Gravity suddenly becomes more complex. The laws we thought were universal become suspect. The foundation of cosmic physics cracks. Dark matter is the invisible scaffold holding the universe together. 5 times more abundant than ordinary matter. 5 times more influential. Yet we cannot see it. We cannot touch it. We can only infer it from gravitational effects. The theory of dark matter emerged in the 1930s when astronomers noticed that galaxies spin too fast. The gravity from visible stars alone cannot hold them together. They should fly apart, but they do not. Something invisible, something massive, something we cannot detect directly holds them in place. Dark matter, the hidden scaffold. For decades, dark matter solved every cosmic puzzle. Galaxy rotation curves, dark matter. Cluster dynamics, dark matter. Gravitational lensing observations. Dark matter explains all of it. The theory became entrenched. It became law. But if the local void exists at the scale we now believe it does, dark matter theory requires revision. The distribution of dark matter must be profoundly asymmetrical. Voids, this massive, require unusual dark matter configurations. The standard predictions for dark matter distribution break down. Some researchers propose that dark matter is not uniformly distributed, that dark matter also forms voids, that dark matter also clumps into filaments and sheets. This is consistent with observations, but it means dark matter is more complex than previously assumed. It is not simply a smooth background component. It has structure, it has texture, it has personality. Understanding this texture becomes crucial to understanding cosmic evolution. This leads to a deeper question. Is our theory of gravity itself incomplete? General relativity has passed every test we have thrown at it, but on cosmic scales, on billion light-year scales, does it break down? Some physicists propose modified Newtonian dynamics, MOND, as an alternative. MOND modifies gravity at extremely low accelerations. In regimes where gravitational acceleration approaches zero, MOND predicts different dynamics than general relativity. Could the local void be an environment where gravitational acceleration is so low that MOND effects become significant? MOND is controversial. Most cosmologists view it as a dead end, but the local void discovery gives MOND new life. If we live inside a region where gravitational acceleration is anomalously low, then MOND predictions might explain observations that general relativity cannot. The bulk flows, the density distribution, the cosmic flows. MOND might accommodate these better than standard gravity theory. Not definitively, not conclusively, but possibly. Other physicists propose that gravity itself is emergent, that gravity is not a fundamental force, but an emergent property of more fundamental physics. In this view, gravity arises from underlying quantum phenomena. At cosmic scales, gravity behaves differently depending on the system's configuration. The local void might represent a configuration where gravitational emergence produces unexpected dynamics. This is speculative, but it is being seriously considered by theoretical physicists. The local void also challenges our understanding of dark energy. Dark energy is the mysterious force accelerating the universe's expansion. We know it exists. We know it is currently dominant. We know it comprises 68% of the universe's total energy density, but we do not know what it is. The most popular explanation is the cosmological constant, an intrinsic property of spacetime itself. But if the local void exists, if matter distribution is fundamentally asymmetrical, could dark energy be asymmetrical too? Could dark energy density vary in different regions of space? This is heresy in modern cosmology. Dark energy is supposed to be uniform, isotropic, the same everywhere in every direction, but observations are challenging this assumption. The axis of evil, a mysterious alignment in the cosmic microwave background that should not exist if the universe is truly isotropic, hints at preferred directions in space. The local void could explain this. If the universe is structured, if voids and filaments dominate, then dark energy distributions might also be structured. Furthermore, the equivalence principle, one of general relativity's cornerstones, might be violated in void environments. The equivalence principle states that the local effects of gravity are indistinguishable from acceleration. In a uniform gravitational field, you cannot tell whether you are being accelerated or experiencing gravity. But inside a void, in a region of low density and asymmetrical gravitational fields, the equivalence principle might break down. This would have profound implications for relativity itself. The cascade of implications is dizzying. Question the local void's geometry, and you are forced to question dark matter theory. Question dark matter theory, and you must reconsider gravity. Reconsider gravity, and you enter the realm of quantum physics and fundamental forces. One discovery creates a domino effect that topples established theories. This is how revolutions in physics occur. One anomaly leads to another. One contradiction requires explanation. The fabric unravels. Yet paradoxically, the local void discovery also offers hope. It suggests that mysteries we thought unsolvable might have solutions. The Hubble tension might not require new particles or new forces. It might simply require acknowledging cosmic structure. The problem was not with physics. The problem was with our assumption that we occupied an average position in a uniform universe. The problem was our blindness to being inside a vast underdensity. Solve the void problem, and many other problems might dissolve. The local void is not just a structural feature. It is a gateway to understanding dark matter, a gateway to understanding gravity, a gateway to questioning fundamental assumptions. And that gateway reveals that our understanding of the universe is far more incomplete than anyone dared admit. The laws we thought settled are provisional. The pillars supporting modern physics are fragile. And the truth, the deeper, stranger truth, lies hidden inside the greatest cosmic void we never knew we inhabited. You are made of star stuff. Carl Sagan said this. It is true. Every atom in your body, carbon, nitrogen, oxygen, iron, was forged in the furnace of a dying star billions of years ago. You are not separate from the cosmos. You are the cosmos. You are the universe experiencing itself. You are matter that has organized itself into consciousness. And now, having discovered the local void, you understand something terrifying. Consciousness emerged not in a random, uniform cosmos, but in a rare, extreme environment. You are the product of a void. A titanic emptiness shaped you. It shaped your stars. It shaped your galaxy. It shaped your destiny. For millennia, humans looked up at the night sky and felt small. We saw ourselves as insignificant specks in an infinite cosmos. We felt humbled, diminished, powerless. We were right to feel small, but we were wrong about the implications. Being small does not mean being unimportant. Being insignificant in scale does not mean being insignificant in meaning. Humans are the universe's way of knowing itself. We are matter that learn to think. We are atoms that learn to ask questions. We are stardust that learn to contemplate its own origins. This is not insignificance. This is transcendence. The discovery of the local void changes how you should understand your place in existence. You do not live in an ordinary region of the cosmos. You live in a void. A region so empty, so rare, so structurally unique that it shaped the very laws of physics as you experience them. You live in one of the universe's most extreme environments. Most galaxies in the observable universe live in denser regions. Most stars exist in cluster-rich neighborhoods. Most consciousness, if it exists elsewhere, probably exists in higher density regions where more structures have formed, where more complexity has emerged. You are rare. Your environment is rare. Your existence is rare. But here is the profound twist. This rarity is necessary. This void is necessary. Without this void, without this low-density region, the Milky Way might not have formed exactly as it did. The conditions that created Earth might not have existed. The conditions that created life might not have existed. The conditions that created consciousness might not have existed. You, reading these words, might not have existed. The void that traps you is the void that created you. The prison is the cradle. The emptiness is what allowed you to emerge. This is cosmology's deepest paradox. Extreme rarity creates the possibility for consciousness to exist. A universe that was too uniform would not create structure. It would not create galaxies. It would not create stars. It would not create life. A universe that was too inhomogeneous would be too chaotic. Gravity would tear structures apart. Voids would be too empty to hold anything. Filaments would be too dense to permit diversity. But a universe with precisely the right balance of voids and filaments, of emptiness and structure, of randomness and order, such a universe can create consciousness. You exist because the universe found balance, and you live in a region that exemplifies that balance. You live in a void that creates possibility. The local void discovery also teaches humility. For centuries, we assumed we occupied an average position. We thought the universe looked the same from anywhere. We were wrong. Our position is special. Not special in the way ancient religions imagined. Not at the center of creation, not privileged by divine design, but special in the sense of being statistically rare, astronomically rare. A galaxy in a void is rarer than a grain of sand on a beach is rare. A conscious being in a void is rarer still. Recognizing this rarity does not diminish us. It elevates us. It asks us to live with awareness that we exist in defiance of overwhelming odds. The implications extend beyond astronomy. If we live in a region where the universe's properties are unusual, where density is low, where gravity works differently, then our observations of the cosmos might not reflect universal truths. Our physics might be local physics, valid in our void, but perhaps not elsewhere. We are like creatures living at the bottom of the ocean. developing physics based on crushing pressure and darkness, then discovering that the universe has air and light. Our cosmology, until now, was void-blind. We were developing physics without understanding that we were developing the physics of emptiness. This suggests intellectual humility. When we encounter observations that do not fit our models, perhaps we should question our assumptions rather than the observations. When the universe contradicts our theories, perhaps the universe is right and we are wrong. This is a simple lesson. It is also revolutionary. Science usually assumes that observations must be re-examined, that errors are in the data. But sometimes errors are in the theory. Sometimes blindness is in the assumptions. The Hubble Tension would have been solved decades earlier if we had been willing to question the cosmological principle. How many other mysteries could be solved by questioning sacred assumptions? Yet questioning comes with responsibility. Understanding that you live in a void, that your environment is extreme, that your position is rare. This creates moral weight. It demands that you protect this rarity. It demands that you steward this consciousness that emerged against such impossible odds. It demands that you treat other consciousness with reverence, whether that consciousness is human, animal, or potentially extraterrestrial. You are not lords of the cosmos. You are custodians of a rare bloom of awareness in a region of emptiness. The universe is still revealing its secrets. The local void is not the final mystery. Beyond the void's boundaries lie other structures. Deeper voids might exist beyond our observation horizon. Stranger phenomena might exist beyond current detection. The universe is larger, older, and more mysterious than we ever imagined. And you, conscious matter, aware dust, the cosmos knowing itself, are part of this grand unfolding. You are not a spectator. You are a participant. You are the universe asking itself questions about its own nature. This is the revelation. This is the meaning hidden inside the local void. You are trapped inside a cosmic void, yes. But that void is not a prison. It is a womb. It is the exact condition necessary for you to exist, to think, to question, to seek truth. The void that traps you is the void that created you. And in understanding this, in accepting this, you transcend insignificance. You become something extraordinary. You become the universe achieving consciousness. You become the cosmos finally understanding itself. And that understanding, that awareness, that revelation is what separates matter from meaning. That is the true revelation that nobody warned us about. We are not trapped in a void. We are the void becoming aware of itself.